A boost converter takes a low input voltage, like 5 volts, and steps it up to a higher output, like 12 volts, without any transformer. Before we look at a real IC, let's first understand this using the simplest possible circuit, just a battery, an inductor, and a switch. Once you understand this basic circuit, the XL6009 IC will make complete sense. At its core, every boost converter works using just 3 components: an inductor, a switch, and a diode, along with a couple of capacitors to keep things smooth. A battery connects to an inductor, and the inductor connects to a switch that goes straight to ground. On the other side of the inductor, through a diode, we have a capacitor and our load. This bare-bones setup is the foundation of every boost converter in the world. Let's close the switch first. When the switch turns on, current flows from the battery, through the inductor, and directly to ground through the switch. During this time, the diode blocks current from reaching the output, so the load gets nothing. But the inductor isn't idle. It's storing energy in its magnetic field, just like stretching a spring and holding it there. Now, let's open the switch. The moment the switch turns off, the path to ground is suddenly cut off. But the inductor doesn't like a sudden change in current. It fights back by releasing its stored energy, and this release generates a voltage spike higher than the battery voltage. This is the core trick behind every boost converter: an inductor's natural ability to produce a higher voltage than what went in the instant its current path is interrupted. This boosted voltage now pushes current through the diode, into the capacitor and the load. The diode acts as a one-way gate, letting current flow to the output while blocking it from flowing back into the inductor. The capacitor smooths this pulsing energy into a clean, stable DC voltage. If we keep repeating this on-off cycle, switch closes, inductor charges, switch opens, inductor discharges into the output, over and over, thousands of times a second, we get a continuous boosted voltage at the output. That's the entire principle. No transformer needed, just an inductor's resistance to sudden current change. Now here's the question. In our simple example, we opened and closed the switch by hand. But how do we control the exact output voltage? And how do we switch fast enough automatically? This is exactly where an IC like the XL6009 comes in. The XL6009 replaces our manual switch with an internal high-speed MOSFET switch driven at a fixed frequency of 400 kHz. That's 400,000 on-off cycles every second. We connect a 47 microhenry inductor, a Schottky diode, an input capacitor to smooth the incoming supply, and an output capacitor to stabilize the boosted voltage. Exactly the same building blocks as our simple example, just optimized for high-speed switching. But there's one more addition: feedback. In our basic circuit, the output voltage wasn't controlled. It would just keep climbing. The XL6009 solves this using a resistor and potentiometer network that constantly monitors the output voltage and reports it back to the IC. Based on this feedback, the IC adjusts its duty cycle, the ratio of switch on time to total switching time, to hold the output steady at exactly the voltage we've set. A higher duty cycle means more boosting. A lower duty cycle means less. The XL6009 has an internal reference voltage of 1.25 volts, and by adjusting the feedback potentiometer, we set our final output. For a 12-volt output, we tune the potentiometer to roughly 2.8 kiloohms. Turn it and watch the output climb. 6 volts, 9 volts, and there, locked at 12 volts. It's worth noting this circuit isn't 100% efficient. Some energy is always lost as heat in the switch, the diode, and the inductor's internal resistance. Even so, the XL6009 manages efficiency up to 94%, which is excellent for such a compact, low-cost IC, and it's part of why it's so widely used in USB-powered gadgets, battery devices, LED drivers, and solar charging setups. So that's the complete working principle behind every boost converter, starting from a simple battery, inductor, and switch, all the way to a fully regulated IC like the XL6009. A switch, an inductor, a diode, and a feedback loop, working together to step up voltage efficiently. Once you understand this core idea, you can apply it to any boost converter circuit out there. If this explanation made things clearer for you, hit that like button, subscribe, and turn on notifications. More circuit breakdowns like this are coming your way. See you in the next video.